welcome to my lecture on concepts of Fourier transforms. We're basically following the content in MRI, the basics, chapter 9, Fourier transform, plus a few other things in here. So you see we've got a lot of material here to cover, a lot of the underlying mathematical concepts that are related to the Fourier transform, including point-spread functions, and also going to briefly talk about the discrete Fourier transform versus the continuous transform. But throughout this lecture, I'm also going to try and really clearly describe how this impacts MRI in particular, and go through some MRI specific examples, so you can really see how this theory applies to this imaging modality. Okay, so first off, I'm going to introduce, first of all, what is a Fourier transform? And we're going to spend a lot of the time here talking about that. But the basic idea is the Fourier transform is going to measure what frequencies are present in some sort of signal. So as illustrated here, it's typically a signal in time, and we're using the Fourier transform to decompose, what different frequencies, what different rates of change are present in that signal. And in addition to the frequencies, we're also getting amplitudes and phases of these associated frequencies. So for example, how strong are the different frequencies, and some phase of the sinusoids. The Fourier transform generally falls under a larger umbrella of Fourier analysis. It also includes Fourier series, the discrete time, and the discrete Fourier transforms. And all of these are some study of the way we can decompose general functions, so any of the f of x, into some sort of trigonometric functions. Okay, so what does Fourier transform have to do with MRI? Of course, magnetic resonance, the phenomenon, occurs at a very specific frequency, and as we've alluded to now in this course, we use magnetic field gradients to actually create these slight variations in the magnetic field across our subject. So this is the case where we have different frequencies. We have different frequencies of the transverse magnetization at different locations, therefore different frequencies in our signal that measure different positions. Okay, so fundamentally, we've got all these different frequencies floating around that we need to assess and decompose. So this is a repeat of some illustration I showed for chapter 2, our introduction to the principles of MRI. And now I've renamed it here, called frequency encoding, which is actually the specific type of imaging that is being done in this example. More details on that in chapter 11. And so, briefly as a reminder, what we're doing is we've got our main magnetic field, B0. On top of that magnetic field, we're adding or subtracting a little bit of magnetic field, and that is going to change the frequency at different positions. And so if we were to look at the net magnetization at two different positions, they're going to precess or rotate at these two different frequencies. We can flip that example into a different direction. In this case, X, use our magnetic field gradients in a different direction, and again, we still have the same effect, and this is actually what we call frequency encoding. So, and then as you remember, the net magnetization corresponds to the signal we receive, so we're going to receive signals with different frequencies. Okay, so back to one of those pictures from one of the earlier slides, where MRI signal is going to come in the time domain, or actually we're going to extend this slightly later into a domain called k-space. And different frequencies in the MRI signal correspond to these different positions because of our gradients. And so then our Fourier transform is actually used for image reconstruction. So in this picture, if we take our MRI signal coming in time, and our so-called frequency domain here would actually, it's actually going to be our dimension in space. So here we might have two different positions that have different resonance frequencies that would show up in the Fourier transform. Okay, so here is the formal mathematical definition that I'm going to use of the Fourier transform. And we will basically be using derived solutions based on these integrals. And the basics of the theory behind the Fourier transform is it says that we can represent basically any function or with some typically reasonable assumptions by these series of sinusoids. So in the formulas here, the sinusoids are the complex exponentials. And then a little bit of terminology. We typically talk about the transform of a function going into the dual or the Fourier domain. And so when we're thinking about like some function in space that might be in millimeters, then our dual domain or our Fourier domain would be in actually inverse units of that. So in spatial frequency, which is inverse millimeters, just saying how fast is something changing in space. Or more commonly we see examples for Fourier transform in time, where a signal might be in time, and then the Fourier transform of that is in frequency with, say, units of inverse seconds for frequency or hertz if the time units are in seconds. Okay, I'm going to go through an example here just to kind of emphasize and hopefully solidify the concepts of these different frequencies. So here, just set up a simple example where we might have two frequencies present in a signal. So the blue line indicates the sum signal of these two different frequencies, a green and a red frequency. And if we took the Fourier transform of the signal, we get something like that, where, like on the right side, where we'd see a peak both at the lower and at the higher frequency here. And for example, we might see a slightly different signal that we take the Fourier transform of. Okay. And we take the Fourier transform, we would see, oh, what's going on here? We actually have a lower amplitude from one of our sinusoids. The green is now the same frequency, but a lower amplitude. The red is the same as before, has a higher amplitude. So not only are we capturing the information of the different frequencies that are present, but how much of these different frequencies are present. And then here's another example where I've slightly manipulated these frequencies yet again. And happened in this case is actually illustrating the phase. So we look at the signal, and this is the reason I've drawn the red line to be negative. We've actually changed the phase of the sinusoid. So let's put these back to back. We see the red curve in the top starts at 1 and then goes down to -1, whereas the red curve on the bottom starts at -1, goes up to 1. They're both a sinusoid, okay, but they have what is called a different phase. So they're starting at a different position within the sinusoid. So we're encoding this information as well. As kind of a brief aside here, one place you see a lot of Fourier transforms is in sound. So sound, there are pressure waves, but we really interpret and create sound based on the pitch, which is our frequency. So we're basically interpreting sound in some sort of Fourier transform domain, listening to a high pitch, low pitch, and for example, if you're any sort of play a musical instrument, for example, the piano, the different keys on the piano are creating different frequencies. To do that, you have to convert the strike of the piano key into some oscillation, which hits the string in the piano, and then that oscillation creates a pressure wave that we can hear. Another example of this is if you use audio equalizers, adjusting the different frequencies, more bass, more treble. It's very much related to the principles of Fourier transforms. Another fun thing I learned, I think it's pretty interesting, is that actually your ear, the cochlea, so this little sort of bony structure that's in your ear canal and is responsible for delivering much of what we hear to our brain, is actually operating quite similarly to a Fourier transform. So we might have here at the left is we have some pressure waves over time that enter our auditory canal. They go down into the cochlea, and the cochlea is designed such that actually the different pressure waves will penetrate different depths. So this red, if this is like a low frequency, might come down deep into the cochlea somewhere and then get stopped. Okay. And when it hits that depth, it actually excites nerves that are at that location, and you get, for example, a little impulse in your neurons at that frequency, that then gets sent off into your brain. You can deal with my poor drawing of a brain there for further processing. If you have a higher frequency pressure wave coming in, it might only travel some shorter distance. It's going to be picked up by nerves that encode then higher frequencies. And so when we're hearing things, when our brain is processing them, it's actually getting some mixture of time information, but really different frequencies are fairly fundamental to how we're processing auditory input. All right, but back to MRI. So I'm going to go through a few examples with some MRI-based examples, where I'm going to walk through a simple object that exists at 3 different positions: the blue, the red, and the green. And we're going to look at actually what the signal would look like from this object. We're going to look at it in the rotating frame. And keep in mind here, so I've drawn this as MXY, the transverse magnetization. This is the source of our signal in MRI. But our receiver coils, we're going to pick up signal from all these different transverse magnetizations. And here's the initial case where we do not have any sort of magnetic field gradient. So all 3 different locations are resonating at the same frequency. They're actually resonating at omega naught, our alarm wave frequency. And when we look at our signal, or demodulate it, as we call it in the rotating frame, it just looks like a constant amplitude when we remove this omega naught component. Okay, and so it turns out if we take a constant amplitude signal, no change over time, and Fourier transform it, we get this, what's called a point object at the center of our reconstructed space. So this brings us to our first important function related to the Fourier transform, which is called the delta function, or sometimes known as the impulse function, indicated here, this little delta. And the Fourier transform of a constant of 1 is the delta, which exists only at 0. So we have 0, only frequency we have present is 0 frequency. So we only get signal after the Fourier transform at this 0 frequency location. So the concept of the impulse of the delta function is we want to represent a value that exists only at a single point. Okay, we don't want some function that's spread out over any sort of distance. Really, the pure mathematical definition is that it exists only at a single point. Actually, the mathematical definition is somewhat complex. It's a very powerful concept. And a couple things I've indicated in the bottom right here in this plot is we can scale the amplitude, so how large this value is by scaling it, in this case capital A. And we can also shift, we can move this impulse or delta function around by, in this case, some value x0. Okay, and we're going to use this delta function more and more in the coming weeks as we get into image formation. Okay, so we started off and all we had was zero frequency. So we got a delta function right at zero, and actually we weren't doing any imaging at that point. We had not applied our magnetic field gradient yet. So in this example, now we want to apply the magnetic field gradient to this simple three-position object. And what we would expect to get in this case is actually a signal like the one that is shown. Now here I'm showing both a real and imaginary component of the signal. This typically interpret as the raw solid or the real component corresponding to mx, the imaginary component corresponding to my. And I think what I'll try to convince you of is if I took the Fourier transform of this signal, what we would get back would be three different locations where we actually have some signal, or in the case of an image, we'd have some actual image intensity beyond black. So let's dig into what's going on in this picture a little bit more. And recall the example from the beginning that when we apply the magnetic field gradient, we're going to get different frequencies at different positions. So actually, what was present in the black signal before was simply the sum of these three different complex exponentials, or these three different sinusoids. We have our red, which is our low frequency, also lower amplitude, so a narrower sinusoid. And it's closer to the center of where we're imaging. Then we have the blue position, which is some intermediate amplitude, and it's also further out in position, so it has a higher frequency. And similar with green, okay, it's also further away from the center, so it has a high frequency rotation, and it's the largest transverse magnetization of all the locations. So its sinusoid is actually the largest as well. And so what the Fourier transform did was it took that black signal previously shown and said, well, we can actually, that is actually the sum of these three different frequencies. And in this example, that's what this would be. We had these three different locations. Each has their own distinct frequency. And these three frequencies will show up in our signal. So this brings us to one of our next set of important Fourier transform, what are called identities or pairs. Okay, and one of these identities says that the Fourier transform of a shifted delta function is going to be a complex exponential, where the frequency of that complex exponential depends on the amount of shift x0. Okay, so what's happening in this toy example, in this object, each of these objects is shifted to a different x0 location. So each of these objects, therefore, has a different x0 frequency when we take the Fourier transform. All right, now we're going to go to another Fourier transform example. Now we're going beyond just having three distinct point objects to saying, well, maybe we have some object, it's now, or say it's uniform, has the same transverse magnetization across some amount of area. So some homogeneous object only exists between point A and point B. We apply our magnetic field gradient. So we're going to get different frequencies corresponding to each of these different positions in this object. And what I'm going to claim is that what the signal would look like from this object would be this kind of squiggly shape, which is peaked at the center and then kind of goes out and oscillates on the sides. And this is, in fact, the Fourier transform of what is called a rect object. So where does this come from? Okay, so we've got our rect object here, and what is it going to be contributing to the signal? Well, at the center location, we're going to have contribution that's at the Larmor frequency, so in the rotating frame, 0 frequency. We're going to have some nearby locations in red that are going to be some amount of frequency away. Now, note here I'm using a concept. We're going to have some, let's call this a positive frequency, negative frequency. So one of these is going to correspond to each of these two sinusoids. Okay, these are complex exponentials, but as you can see, the imaginary component is flipped around. That's what the difference is between a positive frequency and a negative frequency in a complex exponential. Then we can go out to the edge of our object. Also at some positive and negative frequencies. So we're going to get all these range of different frequencies mixed together. Our 0 frequency, plus and minus low frequencies, plus and minus high frequencies, everything in between. But we stop at some limit of the frequencies we're going to get. And if you add all these together, what you get is this, again, this peaked function with these oscillations on the side. And this is a very specific name. This is called the sinc function. Okay, so let's introduce a couple of very crucial functions that we'll use a lot, particularly in the context of when we need to use Fourier transforms. So the first of this I mentioned is called the rect function, which is defined here, and you can find these definitions also in my MRI math concepts notebook or chapter. And the rect function is basically a function that exists for some length and then doesn't exist, is 0 beyond that. And then the sinc function looks like this, and now you've seen this a couple of times. It's sinc of x is sine of pi x over pi x. And the rect function and the sinc function are a Fourier transform pair of each other. Okay, a couple of other points I want to touch on. One is there's a forward and an inverse Fourier transform. And I'll often use these almost interchangeably because they are very, very similar. The only difference between the forward and inverse Fourier transform is the difference in sign. And that's what this set of relationships indicates. If we took the Fourier transform of a function, and we take the Fourier transform again of that function, what we get back is the original function, just flipped in sign. Now with something like the rect and the sinc function, this makes no difference. Right? Flip them around and they look exactly the same. This will make a slight difference when we look at a point object, for example, a delta function that might exist a little positive or a little negative. And what we would see if we took a point object, we took the Fourier transform, we get this complex exponential sinusoid. We take that complex exponential sinusoid and then take the forward Fourier transform of that. We flip our delta function across to the other side. So we just get this sort of flipping effect when we, for example, if you mix up the forward or the inverse Fourier transform. Now, generally, the approach I'm going to advocate for how we use Fourier transforms in MRI is use what are called transform identities or pairs that now I've alluded to a couple times. And here's a list that really covers the key Fourier transform pairs and identities that are relevant for MRI. So we've got at the top our delta functions. We have our rect sinc pair. We have a few other properties: scaling, linearity. We have shift properties, and then the bottom is convolution. So let's go through this example to illustrate one of these properties. Now, what I've just said is that the Fourier transform of, say, this rect drawn on the left is the sinc drawn at the bottom. Now, what happens if we take this rect function and we shrink it? So in this case, we're going to use this scaling identity. And what this basically says is that if we shrink our function in one domain, when we take the Fourier transform, it actually stretches out that function. Sometimes this is referred to as the more is less transform identity. Now, a couple of differences you're going to see in the definitions from MRI the basics and what I've shown here is that I use a unitary ordinary frequency Fourier transform. It has some very nice symmetry properties. If you use a non-unitary with the angular version, you need a extra scaling factor in there. So I prefer this version that I've shown here, as well as a version of the sinc function that is a normalized sinc, not an unnormalized sinc. The normalized sinc has a total area of 1 in the Fourier transform. In this unitary ordinary frequency of the rect is the sinc, as I've shown. Some more information in these very comprehensive Wikipedia pages. Okay, so seeing a couple of these identities here. Now this one on the bottom, I've spoken nothing about except the name. And these last two, we see, well, when we have a multiplication of two functions, say f and g, in one domain, what happens when we take the Fourier transform is we don't get a multiplication. This symbol here, this star, is not a multiplication, this is convolution. Okay, so multiplication in one domain of two functions. There's a convolution in the other domain of two functions. So what is a convolution? Convolution is a little bit of a tricky concept to understand. The mathematical definition here shown in the bottom left and illustrated again with a great Wikipedia entry that what you're doing is you're taking one function, you reverse it, you slide it relative to the other function, then you multiply the two together at each of these different positions, and whatever the result of the two multiplied together, the area of that, so the integral, is the output of the convolution, right? We'll go through some more examples, look at well, what do convolutions look like? But here's the full formal definition of the convolution. But why do we care about the convolution? Convolutions turn out to be pretty useful in calculating this concept that's known as the point spread function, sometimes abbreviated as PSF, or sometimes known also as the impulse response. So the definition of the point spread function is, what is the resulting image when we go through whatever process it takes to create an image. So we have our imaging system, our hardware, other effects happening. We have the experiment. We account for all those, and say we had an ideal point object, okay, an impulse function, just exists at one point in space. We send it through our imaging system and experiment. What do we get out? Do we get out that just single point, or more typically, we get out something that's not exactly that one point, right? We might get something out that if it was a single point, what we get out actually looks like a little sinc function. It's very common. Or we might get something that looks like, well, maybe just a little bit of a blurred out version of our point object. And that would be very common as well. And so this concept of the point spread function is an extremely powerful way to characterize our imaging system, our experiment, different phenomena that might be occurring. So what does this look like in the MRI experiment? So here's an example of that, where I've just taken the previous example, simplified this to single point object at the center where we're imaging, where in the rotating frame, it would just be tipped down and is staying at the same location. It's not rotating at all. And so we get this constant signal, Fourier transform of a constant. It's just a single value at 0. Okay. So ideally, point in, and we get a point out in our image. But I've glossed over something in this example, which is we actually only sample data for a limited amount of time. So I've illustrated that here in the top right, saying, well, I only get to sample or acquire this constant signal for some limited amount of time. Outside of that, I have no information. So we have to assume it's 0. And if we took a Fourier transform as being the way that we're reconstructing our MRI, then now we know we have this rect function. And so what we would get instead of a perfect point object is we'd actually get a sinc object. So in the case of the fact that, well, we can only sample for a limited amount of time, the point spread function of this phenomenon is a sinc function. So how does that example carry out to the case of now back our simple object that exists at 3 positions? Basically, what we'd have to say is, well, actually, we don't get any of this signal here. We get some limited amount of time. What a point spread object would say, well, or the point spread function, concept says, is that, well, each of these point objects is going to turn into little sinc functions. So instead of 3 nice point objects, we get 3 nice sinc functions. Also nice. But they're going to have these little ripples on the side of them. They're not going to be just like a single nice point. They're going to be spread out a little bit. Okay, so a little bit of what is actually going to be blurring in the image, a little of this ringing, sometimes called Gibbs ringing in MRI. It's going to appear in the image due to this limited time sampling, and it's the point spread function that allows us to calculate this. Okay, so now trying to put some of these pieces together. Any change, so that this is basically the definition of the point spread function, any change to this point object during the MRI image formation process is characterized by this point spread function. And we can use this in many ways. It's very powerful. You can calculate changes that happen during the imaging process due to the spin physics like relaxation, doing due to data sampling, so the sampling time or the sampling rate. Things about our pulse sequence design can impact the point spread function, physiology like motion flow, and more. And what happens in MRI is these effects typically occur in the signal or Fourier domain, and they're typically modeled as a multiplication. So jumping up here to our Fourier transform table, we're right in this place right here, okay, where, for example, f could be our signal, what we, or let's call this our true signal, what we really want to measure from our object, and g would account for, g would actually be the Fourier transform of our point spread function. So accounts for other effects, imperfections. And because we have this phenomenon where our signal is multiplied by these effects in the Fourier domain, what we end up with in our image is a convolution in our image domain. All right, so we made it back. Said convolutions would be relevant. And that's because when we have these effects, again, spin physics data sampling that typically are multiplications in the signal or Fourier domain, then they create a convolution in the image domain. Okay, so that was maybe a little more clear to understand in the previous example of the 3-point objects, but what does it look like in the case of this rect object, where now nominally we would reconstruct a rect function and we'd have our f of x is our rect of x, therefore Fourier transform is the sinc, and I'll use this kx notation. The effect of limited sampling is going to say, well, actually, we don't get all this sinc function 0. We just get sampling a part of the sinc function. We just get this region right here. So what we're going to say is that now if we use in the notation of this identity up here, we'd have some sampling function that's actually a rect. And the rect will have some distance w here. So to figure out what's going to happen in the image, we need to know what's going to happen here. It's going to be dependent on this identity. We're going to have to take our original rect function, convolve it with whatever the Fourier transform is of our sampling operator. Okay, but we can figure that out. Well, we've got our rect function, sinc function here. So the Fourier transform, or the inverse Fourier transform of a rect function, is also a sinc function. And then we've also got this scaling identity here, which says it's going to be sinc function scaled depending on how wide we've sampled there. Okay, and put the details here to be precise, showing how we're using a couple of these different identities. And we'll see some more examples of that going forward. Okay, so computing this convolution is not straightforward, but I'll try and sketch out what it's going to look like. And practically, actually, the way you would compute this convolution is probably you would compute the Fourier transform and then compute the multiplication, and then the Fourier transform. Convolutions are generally hard to compute. Fourier transforms, multiplications are easy. Okay, so what we would actually get instead of this nice perfect rect function is we're going to get the borders here, the rect, are going to be a little bit blurred out due to the convolution. So you can think what we're doing is we're taking this little sinc, kind of sliding across this rect function. When it's in the middle, doesn't really make much difference. Maybe we'll see a little bit of oscillation, but when we get to the edge, it's going to start to blur this edge, and then it's also going to create these small rings and ripples. So we have two effects. We have some blurring, and we have what we call ringing as well. Okay, and we can characterize this through this point spread function. Again, just the g of x, and this will apply to not just imaging this rect object, but any shaped object we might have. Okay, to wrap up here, I want to briefly introduce the discrete Fourier transform. And this is important to introduce because actually in MRI, we're always working with discretely sampled data. So we only have a finite number of data points, certain points in space, and so we have to use the discrete Fourier transform, or DFT. And the tool used to compute this is an algorithm called the FFT, or the fast Fourier transform. And the definition here below, if you go back to the earlier definition of the continuous Fourier transform, it's very similar. Primarily, the integral is replaced by this summation over a finite number of points, but we still have this multiplication by each of the points of a complex exponential. Okay, and then this is going to be a quick introduction here, but I briefly want to illustrate a couple of the things and how I demonstrate this. So let's start off here looking at what we have. Fourier transform. Yeah, you might have something that's like continuously valued, and it could actually continue out to infinity. This is the definition of the Fourier transform. Just some function I'm just drawing here, but purposely drawing these continuous valued lines. Whereas the discrete Fourier transform, what's going to happen, and in the bottom here, this would be our data sampling domain, is that we're actually going to only get a limited number of samples here. I represent them by either little stems or little delta functions. They only exist over a limited range. There's only a finite discrete number of them. And it turns out when we take the DFT of this, we're also only going to get a discrete number of samples that exists over some finite range. So outside of the range as shown here, there's nothing out here in the DFT. But for the most part, our identities hold true between the discrete Fourier transform and the Fourier transform. So what's one of our favorite objects? It's going to be the rect zinc pair, and let's extend the lines here for the continuous Fourier transform side here. But if we're looking at the DFT side here, then you might just have a limited number of samples of the rect function. And when we transform this, we're also still actually going to get a sinc function. And that looks something like that. Okay, so we still the basic identities, the shift theorem, the scaling, sinc rect pairs, convolution. These will all actually hold whether we're doing discrete or continuous Fourier transforms. And as a brief motivation, the reason we need to do this is there are analog signals, but we need to compute them to digitized versions of these for computation, for display, and so the concept we'll use for that will be the analog to digital converter. And we'll use the DFT to describe the effects more precisely of our data sampling. And there's two main points here, and these are basically consequences of sampling that, and which is fundamentally related to the fact we have to use the DFT. One is we only sample a limited number of points. So this is actually going to limit the spatial resolution. So that's the example I was showing before, where we only had a limited amount of time we might sample. Turns out that's going to limit the spatial resolution. And we also reconstruct with just, we only reconstruct to a limited range of samples. So there's a limited FOV or field of view that we get for our images as well. Okay, and with that, excuse me, these are the goals I hope you took away from this lecture about the Fourier transform. Then we also talked about convolution, point spread functions, and then briefly discussed the concept of the discrete Fourier transform as well. Okay, thanks for watching.